software. So there were some other programs in here that were kind of researchy. We worked on cognitive systems in the Department of Defense projects and cognitive radio networks. And again, these are all based on UML design. So the point is that here's been my experience in going from no structure for software engineering to a lot of structure in software engineering, and guidelines and procedures and methodologies and tools. You know, the tools for UML is enterprise architecture, Rhapsody. We used, in the early 90s, we used a product that was called Rational Rose. It's now called Rational, and it's distributed and maintained by IBM. And in fact, in the College of Engineering, we have a whole suite of these UML programming tools or modeling tools for software. So think about this, where you're at now in terms of software engineering and software design, because when you get out and you start working, you'll be working in teams that do this kind of work. And these are very key. Web services, I'm going to throw another term out here in a while that they'll talk more about, but service-oriented architectures is a successor to web services, about 2003, 2004. And then this has led to products that are called enterprise service buses, which are software service buses in a distributed computing system, distributed computing environment. These guys here have their origins, like I said, in web services. We had their origins in Corba. There was a big jump from non-structured or non-object-oriented design methodologies in the 80s, in the late 80s, from here to here. And this is where software systems started becoming more reliable. Okay, so that's kind of the background, okay? And now you're designing a system, right? You're designing a software system that's in the project description. So let me give you my view, and then I'll start answering questions of what this software system should look like. We've got a bunch of, I'm not going to call them sensors, but they're actually, some of them are sensors. Some of them may be interfaces, and this is applied to basically for interfaces of some type, and they connect to equipment down here. Okay. And we want to collect all this information. We may have hundreds to 1,000 of these. And if you consider, let's say, an electric utility who's putting out what are called smart meters that read your electric consumption in your home, then you're looking at millions of millions of smart meters that are sensors. If you look at, for instance, Pacific Gas and Electric Southern Cal Edison in the Los Angeles area, they're deploying something like 5 million meters in Los Angeles metropolitan area to read the meters of your residential, commercial, industrial electrical usage. And so they're about halfway there. They've deployed about 2.5 already. And they're getting all this data from the homes and residentials that represents the load consumption at house for each electric user. And they don't know what to do with all that data, because it's, first of all, it's big data, it's massive data, it's terabytes of data, and they have a problem storing it, they have a problem transmitting it, and doing analytics on it. So the problem is that we have this sensor network here of sensors, and then we want to be able to take it and store it somewhere. And we also want to visualize it. So look at this as kind of a multi-level visualization control room or an operations room, where here you may be you're visualizing the smart meter loads. Here you may be visualizing the GIS system that shows geographically where these meters are located. Here you may be visualizing the network management system that controls and manages all these networks that we're going to go through here. Okay. And then you've got processors. And I'm just going to draw, say, a network of processors. That are processing all this data and getting it from, putting it in databases, visualizing it, and doing big data analytics on it. So that's the big picture. Got a lot of data down here in the order of terabytes. You got to store it, you got to visualize it, you got to process it, and do analytics on it. So the question is, what is the software system that sits in between here that connects all these units to the network? Okay. And also connects the sensor network, like this, to the network. And to me, this is what you're designing, kind of a software architecture that represents this, but it includes that, access to that, includes access to processors are there, and then the visualization is there. In our center, what we deal with is we deal with cybersecurity for these kinds of environments. So now you want to make this whole system, including the sensors and the network here, you want to make it secure. And there's a lot of definitions about security here at this level, because you have here you have maybe an RF connection from the sensor to another reader, or maybe an aggregator that is a radio frequency RF kind of Wi-Fi connection. And then you might have fiber optics from here to here. You might have cable. You might have microwave point-to-point connections. So all those interfaces need to be made secure. This network here needs to be secure. And the software system that implements this needs to be secure. So let me just kind of lead you in a direction here that gives you some ideas on where you might want to go with this project. And that's implementing what are called enterprise service buses, which are, as I said earlier, a characteristics a characteristic of service-oriented architectures. Okay, these are products that are built and sold by industry. IBM has them, Cisco has them, Intel has them, Microsoft has them, and a lot of applications like big data centers, they use enterprise service buses inside the system to be able to do all the processing. But these enterprise service buses are just not constrained, say, to a data center. You can apply them and put them and distribute it in any place around the world, as long as you have servers, nodes, and applications. So one of the nice characteristics about these guys is they provide basically a common message transfer through this enterprise service bus between that sensor, which may be vendor A, another sensor which may be vendor B, and another sensor which may be vendor X. So these will all have different APIs on them, application programming interfaces. And so when you take an API for X and an API for B and interface into the service bus, then it does basically a conversion from this format of X to the common format in here. And the common format that's usually traditional in the service buses is based on XML. So there'll be some form of representation of a message as an XML message. You convert it to XML, transfer it across the bus, across the world, to another server, and it gets there, and it comes out here as another API that goes, let's say, to your storage servers, which gets you back in your disk. So, you know, this is one solution, enterprise service bus. You could also use, to implement this network, you could also use web services. And these are, you know, like the .NETs, .NET is the Javas, and all the other stuff that's here. Right? Or you could just do raw programming. You can just do in C, remote procedure, RPCs, remote procedure calls, and do a raw programming part of that. You can do it in C++. And in that case, you're doing a more low-level implementation. You're not taking advantage of all of the tools that have been provided for you by these enterprise service buses in the last 20 years. So think about this as the system that's being described right now for the project. And you guys had a bunch of questions, right? Do you have a copy of the questions that we put up? Any questions on what I talked about?
Right. So I guess we noticed you kind of already described the overall purpose.
Let me say, you want to know why a cruise missile is so lethal these days? When we first did cruise missile, there was no GPS. It was all terrain following radar. And so, you know, you would program the terrain over which the missile was going to go, and these are low-flying missiles so that they stay away from radar. You program the terrain into the missile flies, and it scans the terrain, takes that image and compares it with what's been pre-programmed into the missile, and eventually it finds its target. Okay. Not real accurate in the early stages in the 80s, mid-80s, but when GPS was perfected and it went not only for the government but commercial, then these guys really became lethal because now you use GPS as the guidance system, not the terrain mapping. And GPS is accurate to a couple meters, right, depending on which satellites. how big the receiver is.